Hello and welcome to our unit on oscillatory motion and waves. In this unit, we're going to learn about simple harmonic motion. To begin that, we're going to think about a mass on a spring. If I have this block and I pull out on it, what direction is the force on it? So if I pull the block this way, then the spring exerts a force back the other way. And the opposite is true. If I push the block in, then the spring tries to push it back out. Now let's consider a mass on a string, otherwise known as a pendulum. So if the pendulum swings upward to the side like this, what direction is the force on it? Well, the net force is going to be back down towards the equilibrium position. In both of these systems, we have examples of restoring forces. And to understand restoring forces, what we need is to first understand equilibrium position, which is the position where there is no net force on the object. A restoring force is then a force which pulls an object back towards its equilibrium position. So the net force on the pendulum was back towards equilibrium. The net force, or maybe not net force, but the force due to the spring on the mass was also back towards the equilibrium position. Simple harmonic motion occurs whenever you have a net force that is proportional to the negative of the position. A good example of a restoring force that we have seen is given by Hooke's law, where the force due to a spring is the negative. Here's the position, and remember this x is measured from equilibrium. And K is the spring constant, so it's a proportionality constant. So that has all of the pieces you need for the force due to a spring being a restoring force, and therefore the motion of the mass on the spring is simple harmonic motion. For this, we need a couple of definitions. Displacement we've seen before, but for simple harmonic motion, this is the position relative to equilibrium always. Okay. Amplitude is the maximum displacement for a oscillating object, and a cycle is one complete oscillation. If I think about this graphically, I can think about something that is oscillating like this, where this axis is time, this axis would be position, this would be my equilibrium position, what I'm oscillating around. So anywhere on the x-axis would be the displacement from equilibrium, and the amplitude would be here and here, the maximum distance we've gone from equilibrium. One oscillation you can measure from whatever time you want as your start, but you have to do one complete cycle. So if I start here, I need to go up, come down, I return to my equilibrium position, but I'm now moving downward instead of moving upward, if you will, which means I need to come back around here to get one full cycle. So from our start point to here is one cycle. And if I had drawn this perfectly, from here to here should also be one cycle. And since I drew that one as a solid line with an arrow, I'm going to correct this one. Okay, hope that clarifies those definitions. A couple more definitions. Period is the time for one cycle. Oh, there we go. That's an E. There we go. Time for one cycle. On the previous graph, from here to here, this would be 1 period. And period is usually given by, oops, sorry, wrong way, by a capital T for its letter, its variable. And it is measured in units of time, so seconds would be a good unit for period. But potentially we could be looking at minutes, hours, days, years, any measure of time to get the period of an oscillating motion. Frequency is very much related to period. Instead of it being for the time for one cycle, it is a measure of the number of cycles in a given time. And you might be picking up on this, but it turns out frequency, which is F, is the inverse of the period. So if I have a period of 2 seconds, if t equals 2 seconds, then the frequency would tell me that I have 1/2 of an oscillation every second. Okay. Now, the units of frequency are not typically given as units of 1/seconds. Instead, the units here are hertz, which by definition is 1/a second.